Okay, so I'm ready then.
Okay, let's begin then. Well, it's a great pleasure to welcome Rafael. He's going to tell us about symmetry breaking and 0-1 laws in Minkowski spacetime. Thanks, Rafael. And I think I have 40 minutes.
Right. Normally, so I wanted to mention this is work with Faye Dowker. Can you see my cursor too?
Yes, we can see the cursor as well.
Have to do something like highlight. Anyway, so I'm sure that I won't have time to quite finish. Hopefully I'll get fairly far through. And so I'm giving you these references. The title of the talk is the same as the title of the paper, Symmetry Breaking and 0-1 Laws. And you can find it on my own website, which you just go to Perimeter Institute and look for my website, or archive. But for those who might actually be interested in seeing all the details, I'd recommend my personal website, because sometimes I update things there and I don't get around to doing it in archive. Also, since I don't think I'm going to quite finish, I will actually read the abstract, which I normally would have skipped. So what this talk will be about is two theorems, actually one main theorem and a corollary, to the effect that a discrete subset of Minkowski space-time produced by a Poisson sprinkling cannot break the Poincare group down to a proper subgroup H. What this would mean, if it could break it, that would mean, for example, that it would determine a distinguished rest frame, which of course would be a breaking of Lorentz invariance, or it could be, to take another very interesting example, it could determine a spatial orientation, which in that case, it would mean breaking parity, or in other words, spatial reflection, which is of interest because space-time actually does seem to break it, according to the standard model. So the results that I'll present rule out the most relevant kinds of breakings, but they don't necessarily cover every single case. And I'll raise in the end the question whether or not maybe they do cover every single case, but I have not proven that. Maybe someone knows a little bit of mathematical information that would allow us to say that. The theorem I'll concentrate on rests on a space-time 0-1 law. I'll explain what that means, and it's the part of the title. And I will concentrate on it describing its proof in a hopefully comprehensible way, without assuming any sophisticated measure theory or anything. So as background to this, why am I talking about a discrete or a locally finite subset of Minkowski space? Well, because a lot of physicists now believe that there's some sort of discrete substructure underlying the continuum. And of course, I needn't say that in this conference, where one or another type of discreteness, often a kind of surreptitious discreteness from a non-commutative geometry, if I can say that, is one of the topics of central interest. So the structure I'm talking about, the causal set, which will be the background for my talk, is not surreptitious discreteness, it's in-your-face discreteness. So it's just a combinatorial structure. So if the discrete structure is indeed discrete, if the deep structure of spacetime is indeed discrete, then we immediately have to ask what becomes of all the geometrical symmetries that characterize current physics, the physics of particles and fields, in particular in flat space-time. I believe that even in non-commutative geometry, the same issue plays a big role. in particular, will the translations, the reflections, and the Lorentz transformations, all of which are, the first and third of which are continuous symmetries, be lost altogether, or will they perhaps be reduced to some discrete subgroups of themselves, or possibly broken classically, only to be restored by some form of quantal superposition? The analogy here is a hydrogen atom, which, in terms of its constituents, the nucleus and the electron, cannot be in a spherically symmetric configuration, and yet the wave function, the ground state, is spherically symmetric. Now, all of these possibilities, I believe, have been suggested as ways to restore a kind of invariance that's broken by some form of discreteness. But the surprising thing is that while all of these may be possible, they're not needed. In the case of the causal set type of discreteness, the Poincaré group is actually not broken. That's my claim, and I will try to, in the rest of the talk, substantiate that in a very strong, in what we'll see as a very strong sense. But I probably should give some background on what is a causal set and so on, and what is a Poisson process. So in causal set theory, space-time is supposed to arise as an approximation to a causal set, or possibly a superposition of causal sets in the sense of many causal sets entering into a path integral that defines the dynamics of the theory. Now, this should be true for any space-time, any physically reasonable space-time, but in this case, I'm going to concentrate just on Minkowski space, because Minkowski, four-dimensional, in fact, because it's only in Minkowski space that the notion of Poincaré invariance has a clean mathematical formulation, and we can more easily prove theorems about whether it's broken or it's not broken. So what kind of causal set am I talking about that might break the Poincaré symmetry group? It's one which I'll say, it's another, what this is really asking is what kind of causal set could be the deep structure underlying Minkowski space? And the answer is, from the point of view of causal set theory, that it's a causal set which could have been, although it wasn't, generated by a so-called sprinkling of Minkowski space. Of course, we want it actually to be generated by the dynamics of causal set theory. But as a kinematic question, we want it to have the properties, the twin properties of sharing, in some sense, the causal structure of Minkowski space and determining the volume element also, which together determines the metric. In fact, there's a there's a slogan which I haven't reproduced here of causal set theory, which is that order plus number equals geometry. Equals it, of course, only approximately, but gives it to a very high approximation. So what do I mean by a sprinkling of M4? A sprinkling is the consequence of a Poisson process in Minkowski space that produces a locally finite point set within it, if you like, countable subset of Minkowski space. Poisson process, I assume most people are familiar with the Poisson process. I'll say a little bit more about it in the next slide. But this is a four-dimensional Poisson process, not a one-dimensional one. So you can just think of it, I don't know, am I going to say that? I'm going to say this later, yeah. So the important thing is that we get a subset of Minkowski space, and it inherits from the Minkowski space, from the light cones, it inherits a causal order, and that's all we need to define a causal set, a discrete causal set. I mean, a discrete combinatorial structure that can serve as the discrete underpinning of space-time. So the reason I'm going through this is for the last highlighted or the last sentence in blue, that if I ask what symmetries the causal set admits, I'm really asking the same question about this point set, this set of sprinkled points, omega, in four-dimensional Minkowski space. Now, what is a sprinkling, a Poisson process? What is a result of a Poisson process in Minkowski space? It's just a four-dimensional generalization of the one-dimensional Poisson process in the real line, which is often discussed in terms of cosmic rays. You have a cosmic ray detector, and its world line is a one-dimensional subset. Is like a one-dimensional space-time, if you like. And it clicks at certain times, and those are distinguished moments or points in that one-dimensional space-time. And if they're produced by a completely random process, like we might think cosmic rays falling on a Geiger counter would be, then it's a Poisson process. A Poisson process in four dimensions is just the same thing, except in four dimensions. So instead of thinking of cosmic, you could think of a rain of cosmic rays falling in space-time, or you could just think of throwing darts at a copy of four-dimensional Minkowski space, showing them at random, and where they land, that's a point of omega. So I hope the procedure is fairly clear. What's important for a Poisson process, in fact, what characterizes it mathematically, is that the sub-processes belonging to disjoint regions of space-time are stochastically independent of each other. Whether a dart falls in this region is completely independent of whether another dart fell in this region. And this is, as we'll see, will be the key to the 0-1 law. So let omega be a sprinkling now of M4, little omega. What does it mean for it to break the symmetry group, G, which I'll take to be the Poincare group in this case, the automorphism group of M4? What does it mean, or what would it mean to break it to a subgroup H of G? It's clear that a discrete set of points is not going to be invariant under any element of the Poincare group. So this is not the right way to answer the question, or to ask the question. I'll change it to a physicist's answer. Despite that, it may be that there's an effect of invariance, just as in a fluid, the exact detailed locations of the molecules won't be invariant under translations, but the fluid has translation invariance. So what's a different way to say that is to break it means that we can deduce from it an element of the quotient group, or the quotient, the set of cosets, G over H. I call that X. This I will adopt as what I mean by symmetry breaking. And then we will examine this possibility for different choices of X. So if it doesn't sound that familiar already, let's look at a couple of examples. One of them is spontaneous breaking of isotropy in a ferromagnet. What's X in this case? In this case, X is just the spatial direction, the direction in which all of the magnetic domains spontaneously line up. What's the unbroken subgroup in this case? The group in this case I'll take to be SO3, the rotation group. The unbroken subgroup is the rotations about U. And then the quotient is just a set of possible directions. Okay, that's the simplest case. You could start with a bigger group, and then the quotient group will be bigger. But the important thing is, what is X? X is the direction. The collection of magnetic domains that produce a magnetic field, that breaks the rotation symmetry if you can determine from it a direction. This is also, well, no, sorry, that comes later. Another well-known example of the same kind of thing is in the Higgs-Kibble phenomenon. What is X? X consists of the possible values of the Higgs field. Gauge invariance is a little complicating the story, but the essence of it is the same. So these are a couple of just reminders of what I would mean by X. Now let's return to Minkowski spacetime. In introductions to relativity theory, in textbooks and elementary introductions, Lorentz invariance is often presented exactly this way. It's not saying that there's some group acting that preserves the equations of motion or whatever. Of course, it's often said that way too, but it's very often said, and maybe historically was said even more, Lorentz invariance means that the set of laws of motion and so on, the fundamental dynamics of physics, does not allow you to determine a distinguished notion of absolute simultaneity or a distinguished rest frame. Now, mathematically, a rest frame, just like in the magnetic case, a rest frame is just a unit time-like vector, U. And interestingly enough, on large scales, the cosmic microwave background actually provides such a vector, only approximately, of course, but it has an approximate velocity and that provides a distinguished vector. I suppose some people think that that actually reflects a deep breaking of the Lorentz invariance in nature. I'm not going that route. The question, however, is could a sprinkling of Minkowski space play a similar role? Could it determine a direction? Of course, that's what I'm going to say that is not possible. But if it could, let's say mathematically, what we have to rule out, it means that there's a mapping taking omega, capital Omega, which I'm using for the space of all sprinkling. So it's taking capital Omega to X. So for every sprinkling, it's giving you an element, it's giving you an element of X, in this case, a distinguished time-like vector. And one can think also of X as the unit mass shell, if you like, the hyperboloid of all possible unit time-like vectors. The claim, however, is that no such function can be defined. Now, here's a little enhancement of this theory. Someone might say, well, that's fine. I mean, that's a nice theorem, but maybe only certain sprinklings can break Lorentz invariance and other ones are not. So maybe we should also admit functions f, which are partial functions. They only take certain sprinklings into time-like directions. So in order to leave open this possibility and thereby strengthen this theorem a little bit, I'll claim more precisely that even if there is such a function f, a partial function, its domain has measure 0. In other words, the probability that an actual sprinkling would determine a time-like direction is 0. A second kind of application of the theorem that we will prove concerns chirality. This is, in other words, handedness. Can the sprinkling determine a right versus a left-handedness? This is obviously of interest in physics because reflection invariance or parity invariance really does seem to be broken in nature, or it really is broken in nature, I think we can say. It would be very interesting if this breaking could be traced to some sort of deep structure of space-time, in this case, the structure of the causal set. However, so the question in that case is whether a sprinkling can determine a handedness or spatial orientation. If it could do, there are only two spatial orientations. In this case, the space X would be just a two-point set with elements that I've labeled R and L arbitrarily, since we don't know which is right and which is left, but the two possible orientations. However, we'll find that no such function exists again. Both, of course, parity and Lorentz boosts are elements of the full Poincare group. So these are my claims. Now, how can we prove them? For some reason, it looks like it would be nice to have a single theorem that would cover all the cases. But it appears that different choices of the unbroken subgroup H, in other words, equivalently different choices of X, call for different types of proof. The first type, which applies to the first example, and translations and Lorentz transformations, are both, rests on the fact that there are both non-compact groups with infinite volume, infinite Haar measure, if you like. The second type of proof, which also applies, we'll see what it applies to, but it covers some other cases with some overlap. They both apply to the case of Lorentz invariant. The second type of proof is based on the fact that a certain 0-1 law holds for Poisson processes in M4. The first type of proof seems more useful when H is small, in other words, when X is big, and the second type is more useful when H is big or when X is small. However, I'm going to devote most of the talk to the 0-1 law because it's a more subtle thing in mathematics. Its proof seems more interesting. And for those who are interested in measure theory, it illustrates an idea proposed by Kolmogorov to treat the event algebra as a certain kind of metric space, to put a metric on the event algebra so that you can talk about convergence of events. By events, I mean measurable. So in order to state a theorem precisely, we need a few definitions, so I'll run through them. Omega I've already given you. It's the space of all possible sprinkling, known in probability theory as the sample space. An event is a subset of omega, also a standard terminology from probability theory. The set of all events, all these measurable subsets of omega form an algebra A called a sigma algebra of events. It's called an algebra because it has analogs of multiplication and addition. The analog of multiplication is intersection. That's, I think, a common notation that people are used to. But interestingly, the analog of addition is this Boolean sum, which is called symmetric difference. It's the union minus the intersection of the two sets. And if you want to amuse yourself, you can go through and convince yourself that, in fact, with those definitions, the set of subsets actually does obey the axioms of a ring, or if you like, an algebra, if you include the scalars in Z2. Anyway, that's a detail. Now, the important thing is the probability measure, which takes every event into its probability, the probability of that set of sprinklings. We take that measure to be defined by the Poisson process of unit density in M4. Now, these are all kind of standard. Two definitions that may not be so familiar are and which will be crucial to the proof, is deterministic event and bounded event. A deterministic event is an event whose probability is either 0 or 1. One says that it obeys a 0-1 law. That's the 0-1 law of the title. It's deterministic because if its probability is 0, it's almost sure not to happen. And if it's 1, it's almost sure to happen. So it's deterministic. A bounded event has to do specifically with the Poisson process, and it's one that happens within a bounded region of Minkowski space. In other words, to know whether it's happened or not, you just need to look at the sprinkling in that region. For example, the event, there are more than 5 sprinkled points in that region, is a bounded event. I'll write A0, A sub 0 for the set of bounded events. And finally, this is, I think, obvious. An event is invariant under a transformation of the symmetry group, say a translation, if the translation leaves it invariant. Now, if there's something sort of mathematical interest of this proof, which is perhaps slightly new because I'm not sure this exact theorem that I'll state has been stated for Poisson processes, but the general idea is certainly known. But I think this method of proof, I think, has some interest in itself. And it's based on giving a topology or a metric on the space of events. So because the event algebra is the sigma algebra generated by the bounded events, what does it mean? It means that every event is in some sense a set of unions and intersections and complements of these bounded events. However, that's very abstract and hard to get an intuition for. What seems more useful is the fact that you can define a distance measure on these events such that every event is literally a limit of a sequence of bounded events. And that's going to be crucial. What's the definition? It's the most obvious one if you become used to the whole picture of what's going on here, that it's A plus B, the Boolean sum is a symmetric difference. It tells the amount by which the two events A and B differ, the histories that are in one and not in the other. If the two events are the same, its measure would be zero, because its Boolean sum would be zero. If they're totally disjoint, its Boolean sum would be large, the sum of the two measures. So it turns out that it obeys the axioms for a measure, for a distance. The two lemmas that we'll use that I won't prove here is the first, that taking limits preserves Boolean sum and product. In other words, intersection and symmetric difference. And secondly, taking limits preserves stochastic independence. This is important. If you have two sequences of events, that is sets of histories, sets of sprinklings in this case, and if they each approach their own limits, and if those events are independent stochastically of each other, then the limiting events will be stochastically independent. You could find the proofs in the references. Based on that, we will prove or sketch the proof of a 0-1 law, that if an event, all to do with the Poisson process, if an event is invariant under spacetime translation, and therefore invariant under all the powers of that translation, then it's a deterministic event. Okay. And so all invariant events are actually deterministic. And then as a corollary of this, you'll see why it's a corollary shortly. If the unbroken subgroup, which still preserves the point of X, if it contains at least one non-zero space-time translation, then it's not a possible sprinkling. That sprinkling from G to H is impossible. Now, how does the proof go? The proof of the theorem is tricky because somehow all 0-1 laws have tricky proofs, but its essence can be said in just a sentence or two. The idea is to show that the event A is deterministic by finding two sequences of events, both of which converge to it, but whose members are stochastically independent of each other. Since limits preserve stochastic independence, then A must be independent of itself, which sounds weird. But what it ends up meaning by a one-line proof is that its probability is either 0 or 1. So let me just say the same thing over again, slightly more detailed. So here's our invariant event A. So therefore T, and T is we're taking to be a translation. So all translates of A are the same event. Now take another set of events, which are bounded events, and which converge to A in the distance we define. And for each of those bounded events, let B sub K, another bounded event, be some translation of A by some T sub K, which is just some power of T, which is sufficient. So it's a bounded event. So if you translate that space-time region enough, you'll get a disjoint region. Therefore, that second event will be independent of the first. So we have two sets, two sequences of events which are independent stochastically. The first one converges to A, but I claim that the second one converges to A here too, and here's a very simple proof. Again, a bit tricky perhaps. To say that it converges to A is that the distance between B, K, and A goes to 0, the usual epsilon delta, but the distance that BK is some translate of AK, so that's equal to this. Then the distance of that translate, but the A is invariant, so I can replace A by the translate of A. Any translate of it as itself. So D, that's the distance between these two. But since the Poisson process is itself translationally invariant, the distance between the translated events equals the original distance, which is the distance of AK to A, and that goes to 0 by assumption. Okay. Therefore, the conclusion is that A is stochastically independent of itself. What does it mean? Remember the definition of stochastic independence, which always, at least to me, it always seemed a little subtle or a little counterintuitive. Two events are stochastically independent if the probability of both of them happening, mu of A and A, is equal to this product of the probabilities. Okay, mu of A, B would be equal to mu of A times mu of B. In this case, A and B are the same two events, so it just says, and the intersection of A was itself is A, so it just says mu of A is mu of A squared, of which the only solution, of course, is mu of A equals 0 or mu of A equals 1. So that, therefore, A must be, by the definition of a deterministic event, we've proven that A is a deterministic event. So that's how the proof goes. Now let me illustrate it in two. I think I'm proceeding faster. I must have talked too fast because I'm not going to finish anyway. Okay, so illustrate it with two different possible breakings. The first one is the one I referred to second, which is that the sprinkling omega prefers the left orientation, say what we call left. This is an event that's obviously invariant under any translation, since a translation of a left hand is still a left hand. So by the theorem, that event is deterministic. So what does that mean? That means that any sprinkling will determine either with probability 1, the left orientation, or with probability 0, the left orientation. But it can't be 1, because by symmetry of the Poisson process, not of the individual sprinkling, the probability of getting the right hand has to equal the probability of getting the left hand. They can't both be 1 because 1 plus 1 does not equal 1. So the only possibility is that they both have the probability 0. So they're deterministic and they don't happen. So in other words, a Poisson sprinkling will almost surely not be able to determine a spatial orientation. The second example is the one that I started with, Lorentz invariance. Can the sprinkling select a rest frame? Here, I'm going to sort of skip over this because I think the basic idea is the same. It's just a little more complicated. To say it cleanly, the essence of it is that if it could determine a particular rest frame, it would have to determine every other rest frame with equal probability by the Lorentz invariance of the Poisson sprinkling process. But they can't all be probability 1, so they have to all be probability 0. It's the same argument again. But an important remark here is, so the conclusion is the same. A sprinkling cannot determine an absolute simultaneity or a distinguished rest frame. But an important remark here is that the second result for the Lorentz invariant also follows by method one, which I mentioned earlier but didn't describe. But we sort of just saw it, is that if a sprinkling could determine a time-like direction, then all time-like directions would have to be equally likely. So you would have an invariant probability measure on the unit hyperboloid. That's impossible because the hyperboloid has infinite volume. So you can have an invariant measure, but it can't be a probability measure because the probability of the whole thing has to be 1. So what's interesting here is that that argument doesn't use the fact that it's a Poisson process, but only the fact that it's a process which is Lorentz invariant. We'll see why I say that could be important. And that brings me to the final slide, which is how much time do I need to leave for questions? I don't know. Well, so if no one stops me, I'll finish with this slide then.
The optimal was 5
ruled
minutes.
out. Sorry?
We were hoping for 5 minutes, but it's okay.
Well, okay. Let me say that it raises, I'll just skip over this and say in words, it raises a mathematical question. I've proved the theorem if X has infinite volume or if X contains at least one non-zero translation, but I don't know whether or not that exhausts everything in the Poincare group. But maybe someone does know. If they do, please tell me, and then we would close a possible loophole in the theorem. So let me finish with this observation. In a certain sense, the theorem could be seen as too good because, for a reason I intimated before, which is that it's nice that we don't break the Lorentz transformations connected to the identity because they seem to be very well realized in nature. So, however, it's not so nice that we can't introduce a chirality because space-time has a chirality, perhaps. Certainly in the standard model, it's given a chirality. It has a chirality, but not a local rest frame. If some sort of causal set underlying space-time could have a chirality, but not determine a rest frame, then it would potentially explain CP breaking in the same way that molecular chirality explains the macroscopically observable differences between right and left-handed sugar. So that's a sort of tantalizing possibility, which would require this more general kind of sprinkling process. So I'm just finished with a question. Is it significant then that method one, which rules out the Lorentz invariant breakings, works for any sprinkling process, whereas method two, which ruled out the breaking we might like, makes a stronger assumption. It might be easier to relax. Thanks.
Okay, thank you, Rafael. And it's questions. Here, G.
Okay. Hello, Rafael. It was very
I
interesting.
don't see anyone. Should I stop screen zeroing or whatever?
No,
I don't know what to
could
do.
be.
Okay,
It's
anyway.
better to keep it.
Keep it, okay.
Okay. I have two questions. One is the sprinkling. There are millions of observers. Several observers are there, and each one have their own sprinkling of Poisson sprinkling, which you have started with. Are they union of all the sprinklings?
No, I don't say that each observer has their own sprinkling. Nature is supposed to do the sprinkling.
I see.
I mean, the idea is that nature produces a causal set. It might be, as I said before, a superposition in the sense of a path integral, but just for clarity, let me stick to a single causal set, which is what the the whole discussion was dealing with. It produces a single causal set, and if that causal set is like Minkowski space, then it's something that could have been produced by a sprinkling of Minkowski space. But that's just one possible sprinkling. So that one, observers haven't come into the story yet. So that's just one sprinkling. Of course, you could look at it from different orientations. You know, you could be in a different rest frame. You could be in a different place. You can't reflect yourself so easily, but if you could be reflecting yourself and looking at it from that vantage point as well. And the question is whether it would look different to you if you looked at it in a different place or if you looked at it in a moving frame. And the claim is actually, no, it wouldn't look different. Of course, in fine detail, it would look the same, but that difference would not allow you to actually pick out, this is the distinguished rest frame, or this is the distinguished handedness.
Okay.
Sometimes when does that answer the question? I was just going to embellish on it.
I have one more minor question. Instead of M4,
let me just embellish one.
M4, if you take M6 or some other higher dimensional thing, will you still find a Lorentz invariant space in that dimension?
I didn't hear the first part. Are you asking would this apply in other dimensions?
Instead of M4, if you have a different Poisson process.
Yes, the same proof. The same proof exactly will apply in any dimension, any finite dimension. There's not the same proof, because if you go through it, you'll see all I used is the different regions of the space-time. The Poisson process is stochastically independent, and Poisson processes can be defined in any vector space, any finite dimensional vector space. So it includes all possible Minkowski spaces of any dimension.
Hello, Rafael. Many greetings after a long time.
Hi.
I have two
Happy
questions.
birthday.
Well, I'll call you later, maybe from when I get back to Syracuse. But there are two questions. In quantum gauge series, when there is, for example, in QED, and QCD, there are now a lot of proofs from algebraic quantum field theory people that Lorentz invariance is spontaneously broken. Okay? There's no doubt because it changes. Lorentz transformation.
I didn't hear. Can you repeat the proofs? Let me put the volume up a little.
There are a number of proofs, starting from Tom Kibble and coming down to Froelich, Morchio, Strocki. And recently, a review paper by Bund, Rehn, and Schroer, that Lorentz invariance in gauge series is spontaneously broken.
Oh, yes.
Because of infrared effects, it cannot be implemented unitarily. The transformations cannot be implemented unitarily.
Right.
There's a rigorous. They are rigorous proofs in the sense of algebraic quantum field theory. Now, I'm wondering how your research connect to them. There is this block of research which seem to be to the extent that QFT is correct, which I don't know. Okay. They seem to be quite sure. Second question I want to understand is, what do you mean by stochastic independence? I don't know what it is.
The second one is easy to answer. So it's just what do people call it? If you look in any textbook on probability theory or take a course in it, you'd say that two events are independent in this sense. I'm not sure if another name is sometimes used. If the probability of their joint probability is just the product of their individual probability.
I understand, yes, okay.
That's the notion, right? So it's the same one that says, if you condition on the second one happening, it tells you nothing about the probability of the first one happening. So I thought it was called stochastic independence, but if there's a better name.
It is correlation functions factorized.
Yes, that's exactly what it, well, that's if they were real valued or, scalar valued random variables. But it's the same, yes, it's the same thing. It's the same idea. On the first question, so I'm not sure for two reasons. First of all, you're talking about gauge theories. I was just talking about the
QED, let's take QED.
I mean, the breaking is, and as I understand, you say it's rightly that it's an infrared effect. It's something that has to do with the behavior near infinity of the gauge field, right? If there's a non-zero charge, isn't that the situation? So let me think. To really pose the question properly, we'd want to include the gauge field. It would be quite interesting. This is just a flight of fancy, but it would be quite interesting to have a Kaluza-Klein description of the gauge field, which you can do in the causal set, and see whether a similar theorem could be proven here. But the other comment is, even without having done that, we could, of course, ask, what kind of sprinkling could it be? I'm not totally convinced by what I'm about to say, but if gauge theories, if in nature Lorentz invariance is really broken thanks to the gauge theories, which I'm not convinced is true in a useful sense, but if that's the case, then we would need to look for a more general sprinkling process, a more general notion of, where did I put this? A more general notion of what it means for space-time to approximate a causal set. We'd have to look for a more general notion where there could be causal sets that approximated Minkowski space, but did determine a rest frame, did break Lorentz invariance. And I don't know, I have no idea how one would go about looking for that. And so I'll just reiterate what I said about this. Method one already shows that that's not possible. If your set of possible sprinklings is itself Poincare invariant. So I don't know. I wouldn't be optimistic that there's any simple relationship between what I was describing and this possibility. Is it your impression that in nature, should we go around saying that in nature, Lorentz invariance really is broken? I mean, in the flat space approximation, of course.
No, it's okay. What is the question? I couldn't hear.
Is it your impression that we should be claiming Lorentz invariance really is broke?
Well, how do I know? I mean, QFT, is it a correct theory? I don't know. Okay. Is QED or QCD, are they a reflection of reality? I really do not know. For example, I don't think that people doing functional integrals with Wilson lines are necessarily reproducing QCD. Okay. I don't know, okay, which is correct. But to the extent that QCD approximates reality, it appears that Lorentz invariance is broken, and it is coming from infrared effects, which one can reproduce by calculations. In the context of quantum field theory, strictly avoiding this negative metric states. Okay? That is quite important. Always working in a Hilbert space. Then
I guess one should ask, I mean, just cut me off when we should be stopping this conversation, but one should ask, how would you look for this kind of breaking? Yes. Because if I knew that, then I could try to think what the causal set might have to say about that possibility.
Yes. Despite some opinions, I think it is not true that there are no signals which you cannot measure. In particular, it turns out that the they say the a particular infrared cloud which is determining the superselection sector can be changed, will be changed by appropriate chemical potentials in the evolution operator, and it is actually of such a character generically that all colored correlation functions vanish, and that appears to be a characteristic of confinement. Okay. So
Yes.
there is some indirect. There are other things like this. Okay. There are definitely indirect signals which can be seen. Okay. But whether they are really this is the only way to explain them, I do not know. So there are issues here. But how does your method connect to that? That is what looks to be interesting. I think that Schuster was interested in your work and had some papers trying to produce that in the context of algebraic quantum field theory. And he would definitely know much more than I.
Yeah, he was interested in, I think, different work of ours. He's also interested in causal sets, I think, but that was to do with this so-called SJ vacuum, a certain vacuum that one can define for a quantum field theory. And he was also very interested in the possibility of there being, well, I had written a paper on impossible observables, saying that most observables that you can write down mathematically, you couldn't actually measure by an ideal measurement, because if you could, it would transmit information faster than light. And so he set himself and some collaborators the task of saying, well, what can we actually measure? I'm not familiar with anything, though, in connection with the breaking of Lorentz invariance, but there might be.
Okay. We should move to the next talk because we're
Right.
running behind.
May I make one comment?
Yeah,
and then
please
stop? It appears already from the time of Niels Bohr that to make any connection to this, observe anything, one needs the emergence of a commutative C-star algebra. It is a commutative algebra from the non-commutative algebra of quantum field of quantum theory as we know it. Okay? And it appears also that in QCD, for example, or QED, the breaking of the Lorentz invariance that I talked about, which happens because of events at infinity, very much like in the ferromagnetic case, also at the same time produces a natural commutative algebra which the observers don't connect. And this spectrum actually is a non-separable Hilbert space as required by our friend Giorgio Mirsi, who is in this audience. So something with
Yeah.
stopped.
Let us.
That's it. That's all I wanted to say.
Okay.
Okay. Let's thank Rafael again and move to the next speaker.